A very good morning to each and every one of you joining the session today. It's indeed a great privilege and to and a cordial and a respectful distinguished members, and all the participants assembled session. On behalf of the Department of Computer Application, Integral University, I am pleased to report India and MK domains that is being conducted from 8th January to 21st January 2026. And I am an assistant professor in the Department of Computer, and it's my honor to introduce our esteemed resource person, Dr. Afreen from the application Integral University, Lucknow. She holds a PhD in computer science at Aligarh Muslim University and is an accomplished researcher in artificial intelligence, machine learning, and health informatics. With SCI and Scopus indexed publications, funded research experience, and a strong record of academic mentorship, she exemplifies scholarly excellence and interdisciplinary innovation. Her academic and research make her fully invite Dr. Afreen Khan to kindly commence our session. Over to you, ma'am. Ma'am, I guess you are not audible to us.
Am I audible now?
Yes, ma'am.
Okay.
Yes, ma'am, you are now.
Okay, thank you. Thank you for the lovely introduction, Fiza ma'am. So, good morning, everyone. And my is my screen visible?
Yes, ma'am. Please start.
So, today's session is part of the my topic is next generation healthcare AI multimodal agents with retrieval augmented intelligence, and it's part of FDP on transformative learning through interdisciplinary AI and ML applications in emerging domains. So, in this lecture, we will explore how modern AI systems are evolving to better support healthcare by integrating multiple data types, accessing trusted medical knowledge, and acting intelligently to assist clinical decision making. So, the very first thing that comes to our mind, if we look towards these stats, healthcare generates approximately 2,314 exabytes of data annually, with 80% being unstructured images, consisting of images, text, and signals. So, if we look at a physician diagnosing a patient considers medical imaging that might consist of X-rays, CT scans, MRIs, etc. It could consist of patient history and clinical notes, laboratory test results, vital signs and monitoring data, current symptoms and physical examination, medical literature and guidelines. So think about how a cardiologist makes decisions. They don't just look at an ECG in isolation. They just integrate it with different type of patient symptoms, past medical history, current medications, and lab results. So the challenge is The traditional AI models work on one data type at a time. And our traditional AI systems couldn't do this. They were like having multiple specialists who never talk to each other. That's what we are trying to change. So the evolution of healthcare AI, as you can see, that the era started from 2010, and we are presently we're talking about multimodal RAG-based AI agents. So earlier in 2010 till 2015 era, it was known as traditional machine learning, and the focus was on only a single type of data. Uh, example you can see like predicting diabetes risk using only laboratory values. Then from 2015 till 2020 it was known as a deep learning era. Then came the multimodal foundation models era from 2020 till 2023. Now at present we have the multimodal RAG based plus AI agentic era. Considering these technologies, and if we integrate all these technologies, the multimodal foundation models, the agentic systems, and the RAGs, that is retrieval augmented generation, we can say that the technology alone is powerful. Together, if we just integrate all these things together, they can create systems that can truly augment the clinical expertise. So, what makes this complete integration, this moment special, is that these three technological advancements have matured simultaneously, and these multimodal models let us process diverse data, including all kind of data. So RAG let us stay current with medical knowledge. So this RAG retrieval augmented generation, we can say that it looks towards the medical knowledge. The agents, the agentic AI systems let system reason and act autonomously. And so integrating all these three could create something greater than individually. So the learning objectives are, by the end of this session, you'll be able to understand multimodal AI architectures for healthcare, how these systems integrate imaging, text, and structured data, explain RAG frameworks, how AI systems access and use current medical knowledge, design agentic systems for clinical decision support, that is building autonomous AI systems for healthcare. Next is address reliability and safety challenges, handling hallucinations, bias, and privacy concerns. And lastly, navigate practical deployment considerations. What are the regulatory compliance that you need to look for, interpretability, and integration. So the first thing is, what is actually multimodal learning? Multimodal learning is nothing but the AI systems that process and integrate multiple types of data that we say as modalities simultaneously to make decisions. So the main characteristics of multimodal learning are, it consists of multiple input types. It could consist of text, images, numbers, signal sequences, etc. It can have the joint representation, that is, it learns shared understanding across the modalities, that is, across the different types of data. Next is the cross-model reasoning. It uses insights from one modality to inform another. The next characteristic is unified decision. It consists of single coherent output, that is, and integrating all kind of inputs. So if we look towards an example that like a radiologist who reads an X-ray, right? While knowing the patient's clinical history, not just looking at the images in isolation. So along with the history, along with the radiologist might need the clinical demographics, not only the images in isolation. So the key insight is that clinical decisions are never based on one type of type of data, that is on one type of information. A chest x-ray means something different for a 25-year-old athlete versus an 80-year-old person. So this kind of data, the multimodal AI captures this context automatically. So why does it matter particularly in healthcare? So in traditional AI, in earlier era, we used to have this. If a radiologist see this X-ray, it only shows the consolidation. But in multimodal AI, if we include all these three things in an integrated form, then this X-ray shows consolidation, which combined with patient's fever, elevated WBC count, and history of COPD suggests that is bacterial pneumonia requiring antibiotics. So, talking specifically about the different types of modalities in healthcare with respect to the clinical context. So, the primary modalities in medical AI, we can divide it into 5 parts. We have medical imaging, we have genomic and molecular type of data, we have time series signals, next is structured data, and then we have the clinical text. So in medical imaging, if we talk about, we have different types of images with respect to radiology, with respect to pathology, dermatology, ophthalmology, and it is basically needed for detecting different types of diseases, which consist of images. Next it could the different next modality in medical AI is clinical text, that is all kind of textual data and along with the basic demographics that the patient could have. And third one is the structured data. Structured data, we have the laboratory results, we have vital signs, we have all the demographics and the medical history and the all the kind of medication list, which is initially required. This kind of data is required at the very first stage when something is diagnosed. Next one is the time series signals. As we all know, it consists of time series kind of data. And the last one is the genomic and molecular data, which consists of like DNA sequences and the gene expression profiles, the protein structures, and the metabolomics data. So if we consider these kinds of primary modalities in medical AI, and certain case studies have been presented by Nature Medicine in 2023 and the Alzheimer's and Dementia Journal in 2024. The case study one says that while diagnosing pneumonia, the single modality approaches, there were two kind of approaches that were done, single modality approaches and the multimodal integration. Using single modality, the chest X-ray alone gave this 85.3% accuracy. Clinical notes alone gave the 78.2% accuracy, and the lab values alone gave the 72.1% accuracy. But when the multimodal integration was done, X-ray plus clinical notes plus labs, all these three modalities when integrated, it reached from 72.1% accuracy to 93.7% accuracy. Then it showed approximately 8.4% of absolute improvement. Also, it reduced 55% reduction was found in diagnostic errors. So this was a study done this was a paper published in Nature Medicine in year 2023. Secondly, the next case study was on Alzheimer's disease prediction, and it was done. The paper was published in Alzheimer's and Dementia Journal in the year 2024. In this, when only a single model, only unimodal single modalities were used, then they found that when only MRI imaging data was used, 81% accuracy was found. And when only cognitive data was used, 76% accuracy. Only genetic markers were used, only 69% accuracy. But when all these were fused and when a complete integration was done and a framework was developed out of these three, MRI plus cognitive plus genetic and also clinical and demographic data was included in this, then they got an accuracy of 91% accuracy. So obviously it reached from 69% accuracy to 91% accuracy. So this is we can identify that why such kind of improvement we can see over the time. The complementary information is that each modality captures different types of different aspects of disease. Obviously, we are having a different type of data, MRI, cognitive, genetic. They will capture, these modalities will capture different aspects of disease. The weaknesses in one modality is compensated by the other modality, and they are more robust to missing or noisy data. But if we look towards the clinical relevance of this kind of integration with respect to clinic in medical AI, it shows that how physicians actually think, first of all. Secondly, it reduces false positives and false negatives. And lastly, it handles complex and ambiguous cases in a much better way. So this is the basics of the multimodal architecture, how multimodal models work. The stage one consists of, so there are basically 4 stages. And the stage one consists of modality specific encoders. In this, we have image encoder. And for example, if we give input as chest X-ray, the output will be the image embeddings. Okay. Then it consists of after image encoder, it consists of text encoder. The input will be clinical notes and the output will be text embeddings. Again, in this stage one only, first one is the image encoder, second one is the text encoder, and third one is the structured data encoder. So the input will be lab values and the output will be numeric embeddings. This is the first stage only talks about the modality specific encoders. Now, the stage 2 includes the fusion module. The main purpose of this is to combine all these 3 different modality embeddings that is identified in the stage 1. So the common approaches are in the stage 2. There are certain approaches. First of all is the early fusion, second is the late fusion, and third is the intermediate fusion. So in early fusion, it concatenates raw features. In late fusion, it combines only the final predictions. But in intermediate fusion, the attention-based integration is done, and this is the most effective one. Now, this stage 3 consists of joint representation learning, which creates unified embedding space, then learns cross-model correlations, and it enables reasoning across the modalities that are identified in the stage 2. The last one is the stage 4. It is the task specific head. In this, 3 things are done: classification, generation, and prediction. So classification on the basis of diagnosis, generation is done, and the complete report writing is done, and also the prediction is done in the stage 4. So if we look towards the example of pneumonia detector, so we can see here that from stage 1, X-ray images, clinical text images, and all these are given for a fusion layer. Then it is passed to the classifier, all the modeling and all that is being done in this particular stage, and finally the diagnosis and the confidence level is being checked. So basically, in this, the key idea is that each data type gets processed by a specialized encoder. Like we saw here that in the stage 1, we have different types of encoding mechanisms for image encoder, for clinical notes, and for lab values. So each type of data gets processed by a specialized encoder, and then a fusion module learns how to combine them intelligently, and it is like having different type of and multiple specialists that collaborates on a particular case. So we have different types of, currently we have multimodal foundation models for clinical AI. And these are the first one is the MedPalm, which is by Google Health. Second one is the Checks agent, which is developed by Stanford. Third one is the Lalava Med and Biomed GPT. Then GPT-4V. All these are being used. Next one is mostly these are being used in radiology, pathology areas. So next is the attention mechanisms in multimodal fusion. What is basically attention in multimodal AI? Attention in multimodal AI is nothing but it allows the model to focus on relevant parts of one modality when processing the another. So if you look towards a basic example, when reading patient complaints of chest pain radiating to left arm. So in such scenario, what such multimodal AI will do? In this case, model pays more attention to heart region in ECG and model pays less attention to lung fields in X-ray. So how these model attention works basically, step one is query from one modality asks questions. For example, in clinical context, it will look towards the clinical text. What does this particular shortness of breath look like? Secondly, then it will identify the keys and values from other modality, and it will provide answers. For example, it will look towards the other kind of data, that is chest X-ray, and it will highlight areas showing lung abnormalities. In step 3, the weighted combination creates informed representation, and finally the result will be the model connecting symptoms to visual findings. So this is the attention in multimodal AI. So there are three types of attention in medical AI: self-attention, cross-attention, and co-attention. Self-attention within the particular modality, within the particular you can say a single modality. So image, if you're talking about image, then it will be we will be looking inside the image only. So image patches attending to other patches, and we won't combine here the another kind of modality. Like if we are talking about image, then we can't combine here the textual data or the clinical text. So here the words attending to other words in text. Cross attention means we are combining different types of modalities. It is between two modalities or multiple modalities. The text tokens attending to image regions or lab values attending to clinical notes. The co-attention is the bidirectional. That is, we can only have between the two modalities. Like if we are talking about text and image. So both modalities inform each other simultaneously, and it is the most powerful for medical diagnosis. So this is the example in diabetic retinopathy detection. And there are two scenarios that if we applied this particular concept of attention, so without attention and with cross-modal attention. So without attention, the image, basically this is the image of diabetic retinopathy. In that, the model sees fundus image and it predicts normally and with a accuracy of 89%. But when this particular concept of attention mechanism is applied and cross-modal attention specifically, This is the cross model. The second one is the cross model. The cross model is the attention specifically is applied, which includes the fundus images along with the patient history, and it focuses on the particular this micro neurisms and exudates, and it from 89% accuracy it reached to 94% accuracy. And obviously when we are including different types of modalities, then obviously it will give us the better results, and it will give the better results along with the reasoning also. So next is another example of multimodal radiology assistant, which consists of 5 steps. First is the image analysis, second is the clinical context integration, then multimodal fusion, then clinical reasoning, and then report generation. So now what happens is, now when we are building such type of assistant, or when we are doing such type of modeling, what are the chief input modalities, chief input data that we require in such scenario? So first of all, we would require medical images, which could consist of different type of chest x-rays, that too in a particular proper format. In such scenario we have DICOM format. Next is the clinical context, which could consist of all kind of demographics, patient history, symptoms, prior reports, etc. Next is the structured data. It consists of the age, gender, vitals, lab results, all these things. And along with these type of modalities, we should also have previous studies, that is the historical imaging for comparison. So the first step is the image analysis. When we get such type of data, such type of input, the first step is the image analysis. So we can use for analyzing a particular image, we can use CNN based feature extraction from X-ray. Then it identifies anatomical regions. In this, after identifying all the anatomical regions, it detects potential abnormalities. That is, what could be the potential abnormalities in that particular identified anatomical regions. Then it generates the attention maps. This is part of the very first step, that is the image analysis. In this part, only the image is analyzed in a proper way. Next comes the clinical context integration. In clinical context integration, it processes patient history with medical natural language processing. It extracts every kind of relevant symptoms and all the related risk factors. Then it identifies what could be the key temporal information. So this is the part of this step 2, that is clinical context integration. Next is the step 3, that is multimodal fusion. Now here comes the this part, this types of attention in medical AI, that what kind of data, what kind of modalities we can integrate and we can fuse in order to come to a most probable solution. So in step 3, we have cross attention between image and text, because we are talking about this particular chest X-ray. So cross attention between image and text, because also we are having certain type of input modalities which consist of images also, which consist of basic demographics, clinical context, past history, structured data. So that's why in multimodal fusion we can apply here the cross attention between the image and text. It correlates visual findings with clinical presentation, and then it generates the unified patient representation. Now, next comes the, after the multimodal fusion is done, next is the step 4, that is the clinical reasoning. In clinical reasoning, we have differential diagnosis generation, and it gives us the confidence scoring for each of the finding, and also it gives the comparative values with similar cases. Now, After this clinical reasoning being done, step 5 is the report generation. In report generation, we have the structured radiology report. Then we have highlighted critical findings, and then we have the recommendations to follow up. So this is all in in this particular example, multimodal radiology assistant, which consists of 5 steps, and this is the study that was being done in US, and which they gave this multimodal radiology assistant, they gave name as RAD assist, and it gave a confidence accuracy of 94% with false positive rate as 5.3%. Now, along with advantages, there are certain limitations, there are certain challenges in multimodal learning also. So what are the challenges? The main challenges are the data challenges. And along with data challenges, there comes the technical challenges. So data challenges, as we all know, that the main and the first and foremost challenge in data challenge is the missing modalities. For example, if not all patients have all types of data. For example, like we looked into this particular rat assist, and we tried to include all kind of four types of different types of modality. But even if one type of modality is not present, then obviously it won't build a good framework. It won't and then it won't give a better accuracy and with a proper confidence interval. Right. So first and foremost challenge in such kind of learning is the data challenge, and in that missing modalities is the first is the most important challenge. So the next one is the data imbalance. Some modalities have more samples than others. This is the most important challenge in when we talk about medical data. Next one is the annotation cost. The problem is that it requires expert labels for multiple modalities. And along with these challenges, there are certain solutions to also to these challenges. For example, if we have missing modalities, the solution could be the modality dropout during training, or we have imputation techniques, or we can apply certain robust fusion methods that could handle missing data in the most potential manner. For data imbalance, we have certain solutions. For example, we can apply weighted loss functions, we can apply modality specific sampling strategies, we can also apply the synthetic data augmentation. For annotation cost, the solutions could be the self-supervised pre-training. We can also apply the weak supervision from existing reports and the active learning label active learning. Now, along with the data challenges, we also have technical challenges. First and foremost technical challenge is the modality alignment. Modality alignment in this different modalities have different scales or formats, and the solution could be the learned emitting projections. We can have the attention based fusion and also unified representation spaces. Next one is the computational complexity. In computational complexity, processing multiple modalities, obviously this will be resource intensive. Right? So in this, the solution could be efficient architectures. We can use efficient architectures. We can use modality specific optimization only, and we can also use edge deployment strategies. Now, after the data challenges and technical challenges, because we are talking about the medical AI, so there are certain clinical and regulatory challenges as well. First one is the privacy and security, because we include the patient data. So when we are including patient data, we have the certain privacy and security concerns. The next is the bias and fairness. The models may perform different across demographics, And for example, if we are building certain model or certain framework, it could give a better performance. It could give a better accuracy on a certain set of population, while it could give a lower accuracy on underrepresented populations, because it ultimately depends on what kind of data we are taking. Next one is the validation requirements, and it could be costly and time consuming process because it requires proper approvals. Next, last one is the integration challenges. So while because we have to integrate so many modalities in this while building a proper medical framework, AI framework, so there comes integration challenges. Now, after this multimodal learning, we have RAGs. So the knowledge, there were certain problems in medical AI, and certain problems that were identified, certain challenges we identified here. Now, the traditional AI models, in traditional AI models, when we talk about traditional AI models, we have knowledge frozen at training time. We cannot access new research or guidelines. We do not know what they don't know. That is, uh, in traditional AI models, many models hallucinate plausible sounding but wrong, along with the wrong information. For example, model trained in 2022, right? Now, new COVID treatment guidelines published in 2024. Now, the entire model needs to be changed. The model gives outdated recommendations. Earlier, it was giving 92% accuracy on the same model built. Now, in 2024, it is giving 50% accuracy. So, again, we have to develop from the scratch. So, this could be potentially harmful to patients. So, in such scenario, this is the major challenge when we talk about in medical context. So there comes a technology known as RAG, which is retrieval augmented generation. It is an AI framework that retrieves relevant information from external knowledge sources before generating particular responses. The main idea is, instead of relying only on memorized data, only on memorized training data, we have to look at the model actively searches for the current information. Now, how this particular retrieval augmented generation RAG works. In traditional AI, we know that we just pass the question to the model trained, which consists of trained knowledge. It gives the answer. Now, in RAG system, we will give the question. It will search for the relevant documents. Then this will model the document plus question, and then it will give the particular output. For example, if there is a question, what's the current first line treatment for hypertension? Without RAG, it will give a model recalls all kind of training data that it could have, and it will give it can give any kind of answer. For example, it can give ACE inhibitors or diuretics. Now, this is in the case when the traditional AI systems were being used. With RAG, this will when a similar question, when the same question is asked, what's the current first line treatment for hypertension? And this is being if this is being modeled using RAC systems, it will first of all retrieve all kind of latest guidelines that are being present. Then it will find relevant passages about this particular hypertension treatment. Then it will generate answer grounded in current evidence. That is, according to 2023 AHA ACC guidelines, first line options include ACE inhibitors. This means that it will give every kind of possible answer it could have. right? So what are the key components of RAG? There are basically three parts: the knowledge base, the retrieval system, and the generation model. The knowledge base consists of the medical literature. Here we are talking in the medical context only. So the key components of RAG here, these three components are in context with the clinical data. So the knowledge base consists of medical literature. We can get this kind of info from PubMed and all the related journals. Then we have clinical guidelines. There are different kind of guidelines when we talk about clinical data. Then we have hospital protocols and policies, and lastly we have certain kind of drug databases. Along with knowledge base, we have retrieval system. Retrieval system, it converts questions to search queries. Then it finds most relevant documents out of these four knowledge bases. It identifies the most relevant documents, and then after identifying that the relevant documents, it ranks those documents by relevance. Third one is the generation model. In generation model, it reads all the retrieved documents, then it synthesizes information, it generates evidence-based response to all these documents that has been identified in the stage 2, and then it cites sources. So these are the key components of a RAG system. Now, why it is, what is the benefit of RAG when we talk in with particularly in context with healthcare? So it is, first of all, it is always current. This means that is it accesses the latest research. It accesses that particular knowledge base consisting of all the medical literatures, clinical guidelines, and all the protocols that are being used in a hospital. Secondly, it reduces hallucinations. Why? Because it is grounded on the real documents. We don't have any fake documents here. And thirdly, it consists of there is a transparency. You can show, or you can always show sources because you have the real documents. You have the real sources. Fourth, it is adaptable because you can update knowledge base without retraining. Fifth, it is specialized because it can use hospital specific protocols. And lastly, it is trustworthy. Physicians can verify sources at any time. So you can think RAG as a doctor, like a doctor who looks up the latest treatment guidelines before answering, rather than relying only on what they remember from medical school. So when we are talking about this RAG and all the kind of integrated systems, particularly in healthcare context, this is basically revolutionary for medical AI. Medicine and clinical context is changing constantly, right? So new drugs, new guidelines, new research, new journals, new data, all these databases are just these are continuously changed, and this will continuously change, right? So a model trained last year is already outdated. RAG solves this by giving AI the ability to look things up just like a doctor would consult up to date or PubMed. So the most important thing and the most important challenge is that you need to the first component, that is the knowledge base, should be ready with you. If that is fine, then all the next processes will obviously lead to a better integrated model. So this is the RAG system specifically built for in medical context. So the first is user query. User queries that what are the contradictions for particular here I've written metformin in CKD, right? So this is the query of the user. The step 1 will be query processing. Step 2 will be document retrieval. Step 3 will be context augmentation. Step 4 will be response with citations. So in query processing, in step 1, what we have to do is, with this particular medicine, we have to parse medical entities. That is, in this question, there are two medical entities, metmorphin and CKD. So it will parse two medical entities, that is metmorphin and CKD. Then it will expand what do you mean by CKD? That is chronic kidney disease. Next, it will generate all kind of search queries that will with respect to metmorphin and CKD. Next, it will create all kind of query embedding vectors for metmorphin and CKD. Next comes the document retrieval. In document retrieval, it will search for all the kind of documents that are related to metmorphin, and along with that CKD also. So first of all, it will search for databases, that is vector database search all the kind of medical literature embeddings. Then it will do the semantic similarity matching, and then it will return certain, maybe 5 or maybe 10 relevant documents. Then after retrieving the documents, it will, for example, metmorphin using CKD. This is identified using this particular KDIGO guidelines. These are the 5 documents, because we asked to give top 5 documents, right? Next is the, after retrieving the documents, the related documents, the step 3 is the context augmentation. In context augmentation, we combine the original query. We combine original query. We combine the along with the original query, we combine retrieved document chunks and relevance scores. And along with the relevance scores, we also combine the source metadata, that the source of this particular data, that is the date, the journal, the impact factor, all these things from where it has been extracted. Then we, after the context augmentation, we pass this complete documentation to the for generation. Then we can pass this particular generation to any kind of LLM, that is MedPalm, or any kind of biomed LLM that is being developed. Then it will read the query. It will along with the query, it will read the query and the retrieved context of that particular document. Then it will synthesize the information from multiple sources. Then it will generate comprehensive answer for the query. And the query was the, what are the contradictions in contraindications for metmorphin in CKD. For this particular thing, the MedPalm or any LLM that is being used, it will synthesize information from multiple sources. It will generate comprehensive answer, and then it will add citations to sources. Then lastly, it will give the response with citations, and then this will be the final answer to that particular question that was being asked. And the answer and this answer, metmorphin is contraindicated in patients with all these things. This will be the final answer that our rack system, the medical rack system, the built medical rack system will give. Now, what are the key technical components in this particular model? The key technical components are basically 4. First of all, we have embedding models. Embedding models, as we all know, that what is the purpose of embedding models is to convert the text to numerical vectors. And we have different types of medical options when we talk about when we talk about embedding models. That is, we have PubMed bird, we have BioBird, we have SAPBird, and they are trained. Basically, they are trained on different types of biomedical literature, and they have different type of medical synonym understanding. So now, next one is the vector databases. So in vector databases, in vector databases, we have the main purpose of vector database is to do the fast similarity search over millions of documents. So when we are talking about in medical context, we have so many documents. So we have to identify the relevant document when a particular question is being asked, when a particular query is being done by the user. So we have different type of vector databases. We have Pinecode, we have EV8, we have FIS, we have Milvus. So these are the vector database that makes the medical RAG much more healthier. Next one is the chunking strategies, and this is the key technical component. In chunking strategies, the main challenge is that what is the length of the medical document, and this is the main challenge when we talk about the RAG in medical context. So there are certain approaches to handle such kind of chunking strategies. That is, we can fix fix the size of the chunks. We have semantic chunking. We have overlapping windows. We have hierarchical strategies as well in order to handle the chunking strategies. Next one is the re-ranking. So in re-ranking, we the problem is likewise here when you need to rank the according to the user query, according to the document. So in re-ranking, the problem is initial retrieval may miss context. So the solution is we can go for the secondary ranking, or if again the challenge comes, we can go for the third ranking, unless and until we get a proper response to that particular answer. Now, next is the knowledge basis for medical RAGs. That is, what to include in your RAG system. We have 3 to 4 main components that must be included while building a medical RAG system. That is, first of all, clinical guidelines and protocols. This is must. So in clinical, we have clinical guidelines and protocols. Secondly, we have to include the peer-reviewed literature, and this will come from different the PubMed Central. This will come from the high-impact journals and also from the preprints. That should be used with caution. Next one is the drug information databases. All kind of drug banks, all kind of RX norms, and the National Formulary of India. All these we have to include when we are building a medical RAG system. Along with the drug information databases, we have to identify the diagnostic resources. Likewise, in medical literature, we have certain codes, ICD-10 or ICD-11. So, and what are the disease classifications along with these codes, and what are the diagnostic criteria? Why is it psychiatric or different type of diagnostic criteria? We have to identify that, and we have to identify the resource along with that. So these are the 4 main knowledge sources. First of all, clinical guidelines and protocols, peer-reviewed literature, then drug information databases. Fourth is the diagnostic resources. Along with that, we should have patient education materials. It could include all the kind of demographics as well. And lastly, we have the regulatory and safety data. So the best practices for building a proper knowledge base is that we have to properly identify the data, and we have to properly collect the data. That is, we have to automate all kind of updates. What are the version control? What is the quality curation? And we have to avoid the unreliable websites and also the outdated textbooks. Secondly, after collecting the data processing part, we have to properly properly process the data in order to build a good and healthier rack system, medical rack system. So cleaning and standardizing formatting, extracting structured information, removing all kind of duplicates, enriched with metadata consisting of all kind of data sources, evidence level. So after data processing, we have data organization by how you are organizing your data by speciality or by any type or by recency or by evidence level. So all these things are the best practices, are the healthier practices in before building a proper rack system. So there are certain challenges and solutions, and how to overcome those limitations in healthcare scenario. So the challenge one is the retrieval quality. When we have this kind of challenge, the problem is the retrieved documents may not be relevant, and obviously the impact would be the wrong context, and it will result into the wrong answer, right? So the solutions could be hybrid search. We have to identify through different kind of searching mechanisms, like we can use keyword plus semantic knowledge also. Then we have to re-rank with different kind of strategies. Re-ranking with cross encoders, maybe it could help. Then the query expansion with medical synonyms or the metadata filtering. The next challenge is the conflicting information problem. The different sources may result into different things, and the impact would be model gets confused and it will give inconsistent answers, obviously, right? So the solutions in such scenario could be source ranking by evidence level. Then the data-based prioritization, that we have to give more priority to the recent data in comparison to the old data. Next, we have the conflict detection and flagging, and also show multiple viewpoints with caveats. So in such scenario, we have certain multiple guidelines for different types of target values. The next challenge is the context window limits. So in context window limits, we can only fit limited documents in an LLM, and for such a challenge, we have certain solutions also. We have hierarchical retrieval, we have intelligent chunking, that how to chunk that particular document, how smartly you can chunk that document. And the next solution to this is multi-stage reasoning. You can pass your document in batches also. You can process that thing in batches also. Next is use longer context models. The fourth challenge in building a proper RAG system is hallucination despite RAG. Problem is model still makes up facts even with good context. Why? Because model may ignore retrieved documents or it might fill gaps. The solution to this could be we have to be very strict when we are prompting, and we have to do the citation requirement along with the confidence scores and human in the loop for critical decisions. The next challenge is computational cost. So the computational cost for embedding, for retrieval, and for LNM, it makes everything much expensive. So the optimizations here, we can apply certain optimization strategies. It could be cache common queries, or semantic caching, or batch processing for non-urgent queries, or the tiered approach, maybe 3 tiering or maybe five tiering, depending on the model, what kind of modeling we are doing. So, and the next challenge is the privacy and security. The problem in this challenge is that the patient data is always sensitive to queries. So the solution is on-premise deployment. We shouldn't use any cloud system, and the data anonymization should be done before the retrieval. The differential privacy should be done in embeddings, and the access control on knowledge bases should be imposed, and the audit logs for all queries should be done. Now, this was all about the rack systems, and these were all the limitations and how to handle such limitations. Next, we have the agentic AI. So basically, what is an AI agent? In traditional AI, we have this particular passive tool, and user says, "What's the diagnosis?" and AI just used to give answer, and that was done. Now, we are in the era of agentic AI. AI agent is nothing but autonomous assistant. User says, "Help me with the patient." And now, what is the agent? What is this particular agent word here? It asks clarifying questions. It retrieves the patient records. It searches for the literature. It runs calculations. It suggests differential diagnosis. It proposes diagnostic workups, and it monitors for updates. So it is basically continuous, it is basically autonomous in comparison to traditional AI. So if you have to define what is an AI agent, an AI agent is nothing but a system that autonomously perceives its environment, that is, receive inputs, reasons about goals, that is, it understands the very objective of the problem, it plans actions, it decides what has to be done, and it uses tools, it calls functions, it calls APIs, it searches every kind of thing it can do, it takes actions, it executes plans actually, and it learns from feedback, it improves over time. So the key characteristics of agents are, first of all, it is autonomous. It makes decisions without constant human input. In medical context, example is monitors ICU vitals. It alerts when abnormality is found. Next is it is goal directed. It works towards specific objectives only. If we have to say optimize this, then it will optimize only the particular patient BP control. Then tool use. It can call external functions. It can include call functions also. It can include APIs also. It can do any kind of search. For example, query EHR, electronic health records. It can calculate scores. It can search PubMed also, all kind of journal, all kind of literature that is being present on the internet. Next one is the multi-step reasoning. In multi-step reasoning, the AI agent basically breaks complex problems into steps, and then it try to identify the solution to each of these steps, resulting in a proper output. So, diagnose the if it in medical context, it can divide into diagnosis, then workup, then treatment, then follow-up. So it can divide in numerous steps. The fifth one is the adaptability. It adjusts based on new information. That is, changes recommendation if new lab results arrive. So these are the characteristics of agentic AI. So the next slide is the difference between the agent, the model, and the RAG. If we have simple model, input, it will process it, it will give the output. What is 2 plus 2? It will say 4. Now in RAG system, there will be an input, it will retrieve all the related information regarding that input, then it will process and it will give the output. So for example, what are the if the input is latest diabetes guidelines, it will search for all the related information with respect to the diabetes guidelines. It will synthesize all kind of retrieved information, extracted information, and then it will give the particular answer with respect to the user query. Now, when we are talking about agentic AI, if user gives some input, it will actually it will do every kind of thing, that is, it will retrieve, it will calculate, it will search, it will reason, and then lastly, it will give a proper output. So if the user query is input is manage this diabetic patient, then what it will do, it will retrieve patient data, then it will calculate certain score of that particular patient, then it will search for all kind of drug interactions that could be done, then it will reason about treatment options and propose personalized plan, monitor for changes. This will be the particular output for this particular user query. So why these agents, why we are talking about AI agents in healthcare? Why does these matter so much in healthcare? In earlier traditional workflow, what does a doctor do? Opens 5 different systems, manually searches guidelines, calculates risk scores on paper, and all these being done manually, and then synthesizes everything mentally. So this could take approximately 15 to 30 minutes per complex patient. Next, when we are talking about this particular era, agent augmented workflow, doctor just ask agents to review this patient, this particular patient, maybe this diabetic patient. Now, what the agent will say? It will give the output, automatically gathers all data. First of all, it will automatically gather all kind of data. Then it will provide synthesized summary. It will highlight critical issues. It will suggest evidence-based plan. So all that particular personalized plan, you can say. And the time only 25 minutes review plus decision. This comes under the agent augmented workflow. So there is a huge difference between the traditional workflow and the agent augmented workflow. Now, what are the agent capabilities in medicine? There are certain capabilities of agentic AI when we are talking about agentic AI in healthcare. First of all, information gathering. Second is analysis and reasoning. Next is decision support, and lastly, the communication. How well the how well the agent is giving the output, that comes under the communication. So information gathering, again, the same process, the data collection, the data processing, how we are doing the information gathering, query multiple EHR systems, the all search all kind of medical literature, access drug databases, retrieve imaging studies, right? Next comes the most important part and the challenging part is the analysis and reasoning. Calculate clinical scores, perform risk stratification, generate differential diagnosis, and check if any kind of drug interactions are there or not. Then is the decision support, evidence-based recommendations or the treatment pathway suggestions, or we have to, or the doctor needs to give the dosing calculations and follow up with the scheduling part also. The last part is the communication. It generates the patient friendly summaries. It can also generate the draft referral letters or the discharge instructions, or it can alert the care team to critical findings. So these are basically the key capabilities you can say in medicine. Now the agent architecture and components. First of all is the perception layer. Next is the reasoning engine, that is the LLM part, tool layer, memory system, and then the action layer. So perception layer here, the user queries, the user inputs, and if we are talking about EHR events, if we are having certain kind of electronic health record, then it will include all kind of EHR data, new labs, vital signs, alerts, etc. Then it will also look for any kind of environmental changes there, or if any new guidelines have been imposed or not. Next one is the second stage is the reasoning engine. It will pass this thing into a particular LLM, the medical LLM. It will understand the situation. Then it will formulate the goals. That is, whatever analysis and reasoning part, this will come under the reasoning engine. understanding the situation, formulating the goals, plan action sequences, and then ultimately generating any kind of tool calls or not. Next is the tool layer. So EHR, if we have to apply certain kind of tools, if we are talking about EHR specifically, then EHR query tool, or certain, if we have to identify like this, calculate clinical scores, if you have to identify certain scores, maybe then we have certain medical calculator tools, or if we have to identify certain kind of if we are having certain kind of drug databases, then that kind of tool will be there. Next is the memory system. So in memory system, the what kind of patient, what basically what patient has queried, what user input basically you have given, and it has a this particular thing has a limit, hierarchical retrieval, or it could be intelligent chunking, as we discussed before, that how intelligently you are chunking the long paragraphs, the long document, how intelligently you are passing on to the system that you are trying to build, right? So all this thing comes into this memory system. So lastly we have the action layer. Now, there are certain types of memories in medical agents. We have, because we are specifically talking about medical AI, so we are only including the memory types in medical agents only. So here we have episodic memory, semantic memory, procedural memory, and working memory. So when we say episodic memory means it will store past patient interactions only, right? For example, last visit patient complained of. So only the past patient interactions will be saved in the episodic memory. When we are talking about the semantic memory only stores the medical knowledge. That is all kind of diseases, all kind of treatments. So this is basically the general medical reasoning. And third is the procedural memory. Procedural memory means how to perform tasks. How to perform tasks means to diagnose pneumonia, we have to do this, and this. So in order to diagnose anything, or in order to do something, we have what are the particular steps. So in this procedural memory, this includes procedural memory. Next one is the working memory. Working memory, it basically stores the current task context. So it uses intermediate calculations, it uses partial conclusions, right? So these are the four types of memory types in medical agents. Next is, there are certain patterns when we are talking about agentic AI. First, there are four patterns. First of all, one is the chain of thought. For example, if it is a linear sequence, then it will be like step 1, step 2, step 3. It has to the pattern will be in a proper sequential manner, right? If it is tree of thought means explore multiple reasoning paths. Maybe after step 1, this agent needs to explore the step 3 instead of step 2. So there won't be any particular sequential sequential manner, right? So it will, in tree of thoughts, it will explore multiple reasoning paths, and it will choose best out of those reasoning paths. Reflection, we have self-critic and improve responses. Next is the multi-agent. Specialized agents collaborate, different types of agents, they collaborate and identify for a most probable solution, right? For example, we have diagnosis agent, we have treatment agent, and we have monitoring agent. So we build different types of agents, and then all these multi agents collaborate, and then they can identify and give a proper output. So this is the complete multimodal plus RAG plus agent integration, the complete integration. In traditional systems separately, we used to, if we look towards only the multimodal model, that is, it will analyze only X-ray or notes, or maybe and then diagnosis will be done. If you are talking only about the separately only about the RAG system, then only it will search literature and it will give the recommendations. If only we are talking about the agent separately individually, then it will use the tools and it will gather the information. So this is the traditional system. Now, if we integrate all these systems, which is kind of a healthier approach now in the coming years. So integrated system which can include all the multimodal type of data, all the RAG system and the agentic AI. So this will include everything intelligently. That is, it will perceive multiple type of data, multiple data modalities simultaneously, right? Then it will retrieve current medical knowledge whenever needed, right? Third is the reasoning part. It can reason across all available information, whether it is coming from the multimodal model, or it is coming from the RAG system, or it is coming from the agentic model. Next one is the acting. In acts we can take autonomous actions with tools or without tools. Last is the learn, how well your integrated model, your integrated built model is learning and improving from the outcome individually. If you can compare like multimodal model or RAG system or agent, what is the learning outcome? Or if done in the integrated system, what is the outcome? So this is the healthier, much healthier approach. If an integrated system is built inculcating all these three models, that is multimodal and RAG and agents. Obviously, in multimodal also there will be certain different strategies we have to use. In RAG we have to use different strategies, and in agentic AI we have to use different strategies. In all, when this integrated system will be built, then it will be a much healthier and a much better model performance wise. So these are the architecture and the key advantages and the emerging capabilities. In technically, if you have to look at the architecture part, we have certain layers. We have layer one. Again, that is the same data ingestion layer, which includes all kind of data. Because we are talking about the multimodality here, so data ingestion will include all the multimodal data. Next one is the processing part, where we have to do the data processing, all the fusion part, and all the embeddings part. Next one is the retrieval system. In order to build a RAG system, how we are accessing to the knowledge databases and all. Next one is the agent reasoning engine. It includes all the planning part, using tools and making decisions. And last one is the human AI interface. How a physician or a doctor is reviewing and overriding all these things, all the built integrated model, right? Next one is the what are the basically what are the key advantages of this if we are building this integrated system, whether this is healthier or if we are using separately, that is much healthier. So obviously if we are using the integrated part, that would be much healthier. Why? Because there are certain key advantages, and they are holistic understanding, always current, autonomous operation, transparent reasoning, and it continuously improve. It learns from the outcomes and it gives feedback, personalized care. So there are certain emerging capabilities also when we are talking about the integrated system with respect to agent and RAG and model. So active learning. In active learning, the system identifies uncertain cases and it requests expert labels and it improves over time. Next one is the most and the much healthier part of this integrated. If you have to build this integrated system, is the multi-agent collaboration. We have specialized agents. We can collaborate on complex cases. We can reach to consensus recommendations, and we can learn from the outcomes, and we can learn from the particular feedbacks from the multi-agent collaboration. If we are doing the multi-agent collaboration, next we have the closed loop systems. We can monitor patient responses, we can adjust treatment automatically, and also we can alert whenever intervention is needed or not needed. Last one is the federated deployment. It learns across hospitals, it preserves privacy, which is the most important criteria whenever we are talking about this model with respect to medical AI, and it shares knowledge but not data, right? So these are the real world deployment strategies. First one is the Google Health, and MedPalm is being used in certain hospitals in US, in UK. Google Health is being used. It consists of multimodal LLM along with the RAG that we talked about. It is they have built a integrated system, and it includes multimodal also, and it includes RAG also. Secondly, we have Nuance DAX, which is developed by Microsoft. It is ambient AI, and it includes the multimodal and the agent. So it is not necessary that we have to use all the three things. So in integration we can when we are having these three, we can go for two also, like multimodal or RAG, or multimodal or agent. So this is what they have used, the Google Health and Nuance DAX. The Microsoft has used multimodal and agent. Google Health has used multimodal and RAG. Third, AIMS Delhi, they have developed AI radiology system, and they are using the multimodal imaging along with the clinical text integration and they have deployed in chest X-ray interpretation, also in TB screening for rural areas. Next case study is for the NHS England, and they have built a clinical decision support system. Instead of multimodal, they have combined and integrated this RAG and agent system, and the results are quite good, as you can see from this case study 4. Next one is the case study 5, and again, India Apollo Hospital in India is they are using AI care platform, and this one is the most comprehensive. Why? Because they are using in all the three technologies, that is multimodal, the RAG, and the agents. So this is the healthier and the complete integrated system, and they have deployed in certain labs, likewise cardiovascular risk prediction, in cancer detection, in chronic disease management agents, in patient engagement chatbots. So, and also you can see the results are quite good. 1 million plus patient interactions are there. 30% improvement in diabetes control they have seen. Early detection of 2,500 plus cancers they have identified, and 25% reduction in preventable complications they have identified. So the main key learning in all these case studies, we can say that multi-language support, then critical to training on these patients, on the patient populations. Then it's not necessary that we have to integrate only one, we have to integrate only two or only three. We can go for two, and we can do all the permutation and combination, and build a better and healthier integrated system. But obviously there will be certain challenges and ethical considerations. When we are trying to build certain this type of integrated model, there will be certain technical challenges. And the first thing is the data quality, again, availability. Second, how much the model is reliable, and third, how much your model is interpretable and trustworthy. Next is the ethical challenges. There are certain challenges when it comes to whenever we are talking with respect to healthcare and medical AI. We have certain biases and fairness issues. We have privacy and security issues. Then we have autonomous and accountability issues. Also, the access and equity issues. And the most important challenge are the regulatory challenges that includes the approval and validation, because we are talking about the data, the patient data. So these are the future directions of what we discussed so far. Autonomous diagnostic agents, personalized medicine at scale, cross-model reasoning. This we discussed this I discussed in my earlier slides, and then edge AI deployment. From this, the vision of future healthcare is the coming years. We'll see that we have AI co-pilots in every hospital, preventive health agents, global medical knowledge synthesis. We have democratized expertise, and then we'll be having closed loop care systems. So The key takeaways of this lecture, the most and foremost, the most important points are that we saw that these three technologies are converging, right? Multimodal AI, RAG agents. This combination, this integrated combination is the next gen healthcare AI. This is the very next gen healthcare AI when we will integrate all these three things, right? So working together, we create systems that truly augment clinical expertise. Next, this is happening now. This is not future. Like we saw here, Apollo Hospital is combining all these three things, multimodal, RAG, and agents. So this is not the future. This is actually happening. More than 500 plus hospitals already they have deployed these systems globally. There are certain proven results, better accuracy, the time savings, the improved outcomes. Next, we have to identify one clinical challenge in our surrounding, and according to that challenge we have to build a simple prototype, we have to validate, and we have to then it can scale gradually, right? And because we are talking with respect to the healthcare, there are certain ethics and certain safety measures that we have to include, and they are not non-negotiable. There are privacy, fairness, and transparency issues, and that must be built in from day one. There are certain, and always there will be, we have to maintain this human oversight for clinical decisions, because if we are not the doctors, we have to include them whenever we are building such type of models. Then the Indian healthcare, obviously, it has the huge opportunity, and there are certain unique challenges. And also, when there are certain challenges, we have certain research opportunities. We have better opportunities as well. There are multilingual, resource constraint, tropical diseases at scale. These are the research opportunities currently. And lastly, we have to collaborate, because whenever we are building such kind of model, including all these three type of technologies, and when we are selecting such kind of domain, we have to collaborate with different type of clinicians, with hospitals maybe, and then only we can build a healthier interdisciplinary model. So this was all about my lecture. Thank you.
Thank you, ma'am, for delivering such an insightful and enriching session with us. We truly appreciate your time and expertise and meaningful contribution to this faculty development program. And we hope that your sharing of knowledge has greatly benefited to all the participants who has joined the session today. Thank you so much. Now, I would like to request to all the participants who have joined us today, if you have any query, you can drop it in the chat box with us, or even you can use your mics